Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we will continue our class for propulsion. Okay. I hope you can see my window. Okay. So today we will continue with the final chapter. Okay, inshallah, this is the final chapter, the last chapter for our propulsion course. We're already in 11th week. So this final chapter is a bit different from the rest of the previous chapters because this chapter concerns the rockets, which is a non-air breathing engine. Okay, the previous chapters that we have seen concern the air breathing engine, turbojet, turbofan, and their components, etc. But this chapter concerns on the space propulsion, which is rockets. Okay, so I'm just going to explain a bit. Okay, so actually, this propulsion course will be continue to another course, which is space launch technology. So that space launch technology is the course code EAS 3514. You will take this course during your 6th semester, which is in 1 year to come, inshallah, next year. So this particular course will consist only on the space propulsion. Okay, so that's why in this current course, propulsion, we focus more on the air breathing engine propulsion. But there is one chapter that I've included today, which concerns space propulsion. Okay, so the majority content of our propulsion course, the current course, consists on the non-air breathing engine. Only this last chapter. But this last chapter about the space propulsion will be continued into more detail. You will learn more detail in next year's space launch technology course. Okay, so this course propulsion is the prerequisite to the space launch technology. So you have to pass this course first. Okay. So what we are going to learn today and what I'm going to introduce today in this chapter is only the beginning, okay? Mukadimah, beginning, okay? The detail of the rockets, how the energy, the process of the propulsion, space propulsion, you will learn in more detail next year, inshallah. Okay, so let's start these principles of rockets. Okay, this final chapter, inshallah. Okay, so introduction. So you know rocket engines. Okay, so it's the same. Okay, the principle, the theory is the same as air breathing engine, turbofan, turbojet, etc. So the rocket engine works by action and reaction. Okay, action and reaction. Okay, the Newton's law. So the same. Okay, the principle, the theory is the same. Action, reaction. As long as there is an action force, there is a reaction force. Okay, that push the rockets forward. Okay, push the rocket forwards to a high speed. Okay, so that it propel. Okay. So rockets are lightweight normally compared to turbofan, turbojet, the air breathing engine. Compared to air breathing engine, rockets are normally lightweight. And okay, but they are capable of generating large accelerations. Okay. So the most common type of rocket are the chemical rockets. Okay, chemical rockets. So these chemical rockets use liquid fuel or solid fuel, okay, as the propellant. Okay, so the propellant is stored in the body of the rocket. Okay, and it's a pressurized. It's a pressurized. So we put pressure. Okay. So this propellant can be a single liquid fuel, okay, single liquid fuel, or a combination of a solid combination of fuel and oxidizer. So obviously you have, for a combustion process to occur, you need fuel and oxygen, okay. So the principle is the same, combustion, okay. Okay, so the body of the rocket. Okay, so this one is the example of a liquid fuel rocket. Okay, so liquid fuel rocket, what do we have? We have number one, the fuel, of course, the fuel, oxidizer. So the fuel mixed with the oxidizer, oxygen, so it will burn. Okay, pumps to carry the fuel and oxidizer. Number four, the combustion chamber, where the fuel and the oxidizer is mixed and burned. Number five is the exhaust nozzle. Okay, so that the exhaust nozzle is choked. So we have to have at least Mach number more than one. Okay, at the throat, which among other things dictates the amount of charge produced. So the exhaust nozzle will help the thrust to occur, okay, and the exhaust exit at the nozzle, okay, exhaust exit at the rocket, okay, exhaust exit the rocket. Okay, next one, another one is the solid. Okay, this is the body part of the solid fuel rocket. So solid, for solid fuel you have solid fuel oxidizer, okay, as the propellant, okay, and you have an igniter, okay, to so that the combustion process will occur, okay, and you have a cylindrical hole, okay, in the propellant, act as a combustion chamber. So the hole will act as a combustion chamber, and the hot exhaust is choked at the throat, same as the liquid, and exhaust exits the rocket. So for solid fuel, the different part is that it doesn't have a pump, okay, so it's simply a solid fuel oxidizer mixture, okay, in the body, and a cylindrical hole acts as a combustion chamber. Okay, this is a example. We can skip this one. So rocket engines, like I've mentioned just now, so it employs the principle of jet propulsion, okay, propulsion, and then okay. Okay, okay, with combustive propellants, a chemical reaction, okay. So when you have the fuel and oxidizer in the combustion chamber being ignited, so the chemical reaction will occur and accelerate the hot gas, okay. So by the acceleration of this gas through the engine exerts force thrust, okay, so the thrust will produce. Okay. Okay, how can this thrust occur? Is that this happens because the force, which is the pressure times area, the pressure in the rocket body on the combustion chamber wall is unbalanced by the nozzle opening. So there is opening at the exhaust, and when the pressure area, the force pressure is unbalanced by the nozzle opening at the exit, so the force, the thrust will occur. Okay, the hot gas will accelerate. Okay. At the same time, the shape of the nozzle, the shape of the nozzle also plays a big role. Okay, it helps the nozzle, it helps the rocket to generate force. Okay, by directing the exhaust gas along the axis of the rocket. So the shape of the nozzle also plays a big role. Okay. Okay, so rocket propellant. Okay, rocket propellant is the mass, okay, mass that is stored in the rocket. Okay, macam mercun kan, ada benda dalam tu untuk bagi roket tu, mercun tu bergerak. Okay. Prior to being used as the propulsive mass that is ejected from rocket engine in the form of a fluid jet to produce thrust. Okay, so there we must have propellant, which is a mass that is stored in the body of the rocket. So when there is a chemical reaction, fuel and oxidizer between the in the rocket, So it will produce hot gas, okay, in thrust. So this is the function, some of the example of use of rockets in military, spaceflight, rescue. This one you can read and you know. Okay, rocket engine. Okay, so when the combustion occur, okay, in the body, combustion of the propellant in the body occur, so this will increase the velocity, of course, of the resulting gas to very high speeds. Okay, when the gas, when the pressure increase, temperature increase, so the gas is at high speeds and hence it can produce thrust. Okay. So I'll highlighted here in purple the most important part, but you can read all of this. The effect of the convergent part of the rocket engine nozzle on the high pressure fluid of combustion gas. Okay, so the nozzle plays an important role. So that's why we have convergent divergent nozzle in the rocket. So it can accelerate the gas to a high speed, higher than Mach number higher than 1, right? Okay, to cause the gas to accelerate to high speed. Okay, the higher the speed of the gas, the lower the pressure of the gas acting on that part of the combustion chamber. So this is the theory of Bernoulli. Okay, remember Bernoulli. If we have high velocity, so a high velocity, lower pressure of gas, and vice versa. Okay, the speed and the pressure is not proportional. Okay, indirectly related. Okay, the flow will reach Mach 1 at the throat. Okay, it has to reach a Mach 1 at the throat so that it can increase to supersonic velocity. Okay, remember you have learned in the aerothermodynamics, even I have explained a bit before, in order for a gas fluid to reach a supersonic flow, we need to use convergent divergent nozzle. We cannot use just convergent nozzle. Convergent nozzle. Remember, the fluid, the flow will be choked at the throat. Choke means limited, right? I have explained. So it can't be increased anymore. So we need another divergent nozzle. So it becomes convergent divergent nozzle to increase the velocity of the gas to a supersonic speed. Okay. For every action, there is an equal and opposite reaction. So this is the same, the Newton's law theory, principles. Rocket thrust is caused by pressure acting on both the combustion chamber and nozzle. So this is the force pressure just now. We have a force when the combustion process occur. The gas will will increase pressure at the wall of the rocket body. Okay, so this pressure will act along the body at the combustion chamber of the rocket. So so once we the exit exhaust nozzle is open, then it will this thrust this force will act forward. Okay, so that rocket will accelerate. Okay, I'll show you the diagram. Okay, this one maybe you will understand clear. So okay, once the combustion chamber combustion process occur, okay, the gas, the fluid inside the rocket body will act on the wall, okay, of the rocket body. Okay, it will increase pressure on the wall. Once the exit of the exhaust nozzle is open, then the thrust, the exhaust speed gas will produce an reaction action backward, and due to the Newton's law, it will cause an action reaction at the front. Okay, this action reaction. Oh, you can say opposite. Okay. Okay, so rocket thrust is caused by pressure acting on both the combustion chamber and nozzle. Okay, so you have pressure acting on the wall. So this pressure acting the wall, once the exhaust is open, so this gas, this opening will permit the exhaust gas to have an action. Okay, we read this. In a closed chamber, the pressure are equal in each direction and no acceleration occurs. Okay, if the chamber is closed, there are no acceleration occurs. The pressure only act equal in each direction. If an opening is provided in the bottom, if you open at the exit nozzle of the chamber, then the pressure is no longer acting on the missing section. Okay, this opening permits the exhaust to escape. So escape in this direction. The remaining pressure give a resultant thrust. So action, reaction. Okay, so this reaction become the thrust force on the side opposite the opening, and this pressure are what push the rocket along. Okay. At first the force pressure acting on the wall, okay, and then once the opening, the pressure will no longer acting on the wall. Okay, it permits the exhaust to escape, and then as a result of that, we have a opposite action. Okay, so this one also the same. Just to explain, in this shape of the nozzle. Okay, so you need to have convergent divergent nozzle to give more force. To accelerate the gas to higher kinetic energy. Okay. So to maintain the thrust, okay, so we need to add continuously the propellant gas inside the combustion chamber. Okay, so the rocket will continue to move. Okay, so according to Newton's third law, as I've mentioned just now, and from the conservation of momentum, okay, so from the conservation of momentum, okay, we will characterize how much momentum increase is created for a given amount of propellant. Okay, so as for turbofan, turbojet engine, the main parameters are thrust force, propulsive efficiency, right? But for a rocket engine is normally characterized in terms of a specific impulse. The specific impulse parameter is more important for rocket engine. Okay? We will still calculate the thrust, but the characteristic of a rocket engine is determined by their specific impulse more and the velocity. Okay, those parameters are more important for rocket engine. Therefore, the faster the net speed of the exhaust in one direction, the greater the speed of the rocket can achieve in the opposite direction. Okay, so another important parameter is the speed of the exhaust. Okay, the speed of the exhaust. Okay, so these are the force acting on the rocket in a flight. So we have the same as the aircraft engine, except that the direction is a bit different. So we have these four force. So we have lift, we have drag, thrust, and weight. Okay. So basically, the drag and weight acting on the same direction, kind of the same direction below, and the thrust has to be higher than the thrust force has to be higher than the sum of the drag and weight, so that you can push the rocket forward. Okay, so thrust from the engine, gravity from the bodies, drag if moving in atmosphere, lift usually relatively small effect. So for a rocket engine, the lift force normally is quite small compared to the drag, weight, and the thrust. Okay. This force with a stabilizing tail present will, unless deliberate control efforts are made, naturally cause the vehicle to follow a roughly parabolic trajectory termed a gravity turn. Okay, so due to this force and the shape of the rocket, so the rocket vehicle will usually follow a parabolic trajectory. Okay, parabolic, parabolic trajectory, and turn a gravity turn. Okay, that is normal. Okay, drag. So drag can be minimized by an aerodynamic nose cone, keeping the rocket's angle of attack as low as possible. So that's why, in order to minimize the drag force, okay, so that we can, the rocket can fly higher. So we need to minimize the drag force, right? So the drag force can be minimized by an aerodynamic nose cone. So that's why the rocket will have like a nose cone like this. Okay, the shape of the rocket, you have a cone like this because you want to minimize the drag. Okay. 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 Here comes those performance parameters for a rocket engine. So number one, we have thrust. Of course, we have net thrust. So the net thrust for a rocket engine is simple than the air breathing turbojet turbofan equation, right? Because the initial velocity of a rocket engine is zero. Okay, if the rocket engine doesn't move, so the initial velocity is zero. Okay, so that's why we only have this first term. Okay, this term. Okay, the exhaust velocity, which are further called effective exhaust velocity, VE. Okay, so this is very important parameter, VE, effective exhaust velocity. Okay, and plus the rocket engine doesn't have air mass flow rate, only have the mass of the propellant. Okay, so very simple. Okay, based on the momentum. Okay, so the net thrust for a rocket engine is only this term. Okay, because it doesn't have an initial speed. Okay, so next, this is a total impulse. Okay, so total impulse of a rocket burning its propellant is, okay, so first impulse. What is impulse? Impulse is defined as a force acting on an object over time. So it relates with times, massa, time, right? Okay, so um, uh, uh, impulse is the force acting on an object over a period of time. So this is force multiplied with time. So this is the total impulse of the rocket engine. Okay. Specific impulse. Okay, this is what I've said just now. The most important parameter for a rocket engine is specific impulse, because specific impulse is has a units of seconds. Okay, so it is characterized by this equation. So you need the exhaust effect. It relates with effective exhaust velocity. Okay, so why this value is important? Because we can calculate we can calculate the exhaust velocity, the speed. That is the most important part, because for a rocket engine, we need to know how fast it can go. So the velocity parameter is very, very important. So that's why this parameter is important, because we can calculate the effective exhaust velocity. Okay. So that's the greater the specific impulse, the greater the net thrust and performance of the engine. So we try to achieve a higher specific impulse as possible. Means higher specific impulse means a longer means high specific impulse is measured in seconds. Means that longer the period of time that the rocket can be launched. Okay. So that's why the greater the specific impulse, the greater the net thrust and performance of the engine. So better the performance. Okay, we try to achieve a higher specific impulse as possible. So higher specific impulse cause a higher exhaust velocity, means dia lagi laju. Okay. Delta V rocket equation. Okay, this is also another important parameter. Okay, I think you have learned this one in space mechanics. Okay, the Tsiolkovsky Tsiolkovsky susah sebut, rocket equation. Okay, so which is actually the delta V rocket, is also named as delta V rocket equation. So what is delta V? Is the capacity of a rocket, okay, which is the total change in the velocity of the rocket. Okay, total change in the velocity, and it depends on the initial total mass and the final total mass. Okay, because for a rocket engine, the final mass is of course lower than the initial mass, because throughout the trajectory of the rocket will lose the mass of the propellant. Okay, because the mass of the propellant will be burned, okay, in the combustion chamber, so it will lose weight. So the final total mass of the rocket engine obviously normally will be less than the initial total mass. Okay, so this is the delta V that we calculate. So delta V links the effective exhaust velocity with the ratio of the mass. Okay. Okay, so this is example graphic of delta V rocket equation. The mass ratio depends on the delta V. Okay, so it increase like exponentially like this. Okay, mass ratio. Okay, the mass ratio, which is the ratio of the initial to the final mass. Okay, so for any burn, the ratio between the rocket's initial mass and its final mass. Okay, a high mass ratio is desirable. Okay, for good performance. So, in order to characterize that the performance of a rocket engine is good or not, okay, so if we have a high mass ratio, means that the initial mass is a lot higher than the compared to the final mass, then that means that we have a good performance of engine. Means that this indicates that the rocket is very lightweight and hence performs better. So we try to achieve a lightweight rocket as possible. Okay, so if the ratio of the rocket is higher, the mass ratio is higher, which means the mass ratio is higher, means that the initial mass is a lot higher than the final mass. Okay, means that we doesn't carry too much propellant. Okay, if the mass ratio is high, which means that the initial mass is a lot higher than the final mass, which also means that the rocket doesn't need too much propellant, so that we save fuel. Okay, this permits the carrying of even more propellant, enormously improving the delta V. Okay, so less propellant improve the delta V, because the delta V just now relates the ratio. So if this ratio is high, so delta V is higher. Okay, so increase the velocity. Okay, so that's why it is said to be perform better. So higher mass ratio are generally achieved with liquid rockets. Okay, better than liquid propellants, better than solid propellants. Okay, staging. Okay, what is staging? Staging actually involves dropping off unnecessary parts of the rocket to reduce mass. Okay, so in order to design a better performance of a rocket engine, so scientists have include this process, which is called staging. Staging means we drop unnecessary parts of the rocket throughout its trajectory, okay, to reduce mass in order to for the rocket to be more lightweight, okay, so that it can perform better. It can goes faster, okay. When of take take a particular minimum percentage of takeoff mass that is too great for the propellant, it carries to achieve that delta V, okay. So how to solve this problem? This is the problem, the initial problem. So how to solve it is by doing the staging. Solved by staging, the rocket sheds excess weight. Okay. So we don't want the extra propellant mass, because extra propellant mass will prohibits us from achieving a higher delta V. We don't want low delta V. We want high delta V. So we need to lose some mass of the propellant, mass of the rocket engine as well. However, the payload can be carried goes down geometrically. Addition delta V for each stage is simply additive. Okay. Okay. Energy efficiency. So another parameter that can be used to characterize the performance of a rocket engine is of course, efficiency. So the efficiency for a rocket engine is calculated by this from this equation. So it is the ratio of the power produced. The power produced, of course, is the kinetic power, the velocity, right? This is kinetic power, kinetic energy over the combustion energy, the thermal energy produced by the combustion chamber. Okay, so output over input. Okay, normal energy efficiency. So energy efficiency, the definition, the heat energy from the combustion process is converted into kinetic energy. The power, kinetic power, the velocity of the rocket. Okay, high efficiency rocket combustion can be performed at very high temperature. Okay. However, rocket vehicles are extremely inefficient at low speeds. So scientists design rockets purposely for high speed. The rocket is not for the function is not for at low speed. It will be inefficient. So that's why for low speed we maintain with normal aircraft engine, turbojet, turbofan, etc., turboprop, etc. But because the rocket vehicles are designed particularly for high speeds flow. Okay, otherwise it will be inefficient. Okay, example like this. For example, okay, this is just example. If we calculate the energy efficiency, okay, so example, if we have energy efficiency of 0.7, 70%, okay, 0.7, or rocket flying at Mach 0.85, which most aircraft cruise at, okay, for example, if the Mach number of the rocket is 0.85, which is this is the normal value for aircraft cruising, with an exhaust velocity of Mach 10, but the velocity is very high, right? We'll have a predicted overall energy efficiency of 5.9%. Okay, whereas a conventional modern air-breathing jet achieve closer to 35% efficiency. Okay, this is just to show you example that rocket vehicles is inefficient at low speed. At low speed, we still maintain using the air-breathing jet engine. Okay, because this to say that a rocket, if you use a rocket at low speed at Mach 0.85, but rocket, being a rocket, it has an exhaust velocity very, very high, which is, for example, at Mach 10. So it is very useless, okay? It can only create energy efficiency 5.9%, which is only 6%. Otherwise, whereas if we use the conventional air-breathing jet engine with this Mach number 0.85, we can have an efficiency 35% for the same situation. Okay, so thus a rocket will need about 6 times more energy, which is very unuseful. Okay, so that's why a rocket vehicles is extremely inefficient at low speeds. Okay, it is used for high speeds. Okay, that's all. So next week, inshallah, we will look into the tutorial. Okay, we will apply all of these parameters: energy efficiency. What else? Okay, the delta V rocket equation, specific impulse, net thrust. Okay, we will use all of these parameters to evaluate the performance of a rocket engine. Okay, so we will see each other next week, inshallah, during tutorial. Okay, thank you very much. That's all from me. Okay, so I hope you understand and you can learn something from this. Okay, thank you. Assalamualaikum.